Applied Physics Homework 72, Mr. Gazda here. This is on torque. So, this is a typical setup here. Here's the, it's like a lever setup, or you can call it like a seesaw kind of setup. The thing that it will pivot on is called the fulcrum, know that. Rotational equilibrium is when both sides of the lever and fulcrum setup are in balance, which means it'll be balanced and it won't, the rotation is around here, so it could rotate this, it could go like this or like that, so that's when they are balanced. And torque, to calculate torque, it's the mass times the torque arm, and this is on your reference table. Our tricked out version, we included it up here. So the mass, we're doing weight here in pounds, and the torque arm is the distance from here to, I'm using the center of the mass. That's what torque arm is. So torque arm for this weight here, that's the torque arm of this weight to there. The torque arm for this is here to here. So basically, the longer the torque arm, the more force you will apply, basically. And then the different weights will determine what that is. So here we go. Calculate the torque of the 10-pound weight. Torque of the 10-pound weight. So torque is, and I recommend you write the torque equals mass, which is going to be 10 pounds, times 3 feet is the torque arm, 3 feet. Well, 10 times 3 is going to be 30. Now, for the units, check out the units. This is what you want to do. Pounds times feet, okay, which is going to be like pounds times feet. We often do it like this, foot, pounds. And you could do it like this, foot times pounds. You could probably do it like this, foot times pounds. I think I often do it as foot. So the real word they use is foot pounds. How many pounds per force multiplied by feet, basically, foot pounds. And if you buy a torque wrench, that's what the measurements are, foot pounds. Okay, calculate the torque created by the 3-pound weight. So 3 pounds, it's 8 feet is the torque arm. So it's basically just 3 pounds times 8 feet. 3 times 8 is 24, and that's again foot pounds. 24 foot pounds. So this is 24, that's 30. Would the setup above be in rotational equilibrium? These would need to be equal, so the answer is no. And then the question is, so this here creates 24 foot-pounds, and this is 30 foot-pounds. Sorry, foot-pounds. So which way would it tip? It would tip this way. This side would go down, and this side would go up. To make an equilibrium, you have to add more weight, or if this was extended out and push down on it. Okay, so this is just really the basics of torque. Calculate the torque created by the 14-pound weight above. Again, torque equals torque arm times mass. And we're using weight here, and that's going to be 5.5 feet times 14 pounds, and that is 5.5 times 14, 77. So the answer is 77 foot-pounds, and that's just how I'm saying it. It's really foot. It's foot times pounds, but foot-pounds. Okay, that's the answer there. Foot-pounds. On to the back. Here we go. On to the back. And here I have a wrench. So you create a lot of torque with the wrench to loosen that nut. So what I have here, on this wrench, on this nut, I said 38 pounds of force applied this way. Okay? And then you just 0.75 feet from the nut is where you'd put your hand to put the force down. So the torque would be weight, or I'm going to say even the force in this case, which weight is a force, so this could be the force in this case, times the torque arm, and that's going to be 38 pounds of force times 0.75 feet equals 28.5 foot. Maybe I'll write it like that. Foot-pounds is how you say it. Okay. Now, to get more force on a wrench, if that is all you can apply, and it doesn't come loose, you want to get a longer wrench. You get a longer wrench, you put the same amount of force, it will create more total force and loosen the nut. If you have another concept of a cheater bar on a wrench, that is what that's about. Calculate the torque created by the 200-pound weight, which is basically 200, 1.2, so it's going to be oh, I'm sorry, I made a mistake. 200 pounds times 1.2 feet will give us 200 times 1.2. 200 times 1.2 is 240. 240 foot-pounds. Okay? And then you have much longer torque arm here. Now, just because I drew it that way doesn't mean it's balanced. It's just how I drew it. That's one of the questions here. So now this is going to be 22 pounds times 14 feet, and that will be, if you do 14 times 22, that gives you 308 foot-pounds of torque. Foot-pounds of torque. Okay. Would the setup above be in rotational equilibrium? These forces, the torque around this point, would need to be equal, so the answer is no. Toward which side would the stick tip? Okay, well, so this has more force, even though it's much less weight. So in this case, 22 pounds can get more torque than 200 pounds, which is kind of what I'm trying to get at here. It would tip towards the 22-pound side. 22-pound side, or maybe you put left side. Okay? So, this basic intro to torque, we're really going to use this coming up. I'm Mr. Gazda, and I approve. Oh, that's upside down. I approve this homework upside down.